I want to talk a little bit about the symmetric group and multiplying permutations. So I don't want to do all the details here. I highly encourage you to read section 1.3 of Dummett and Foote, where they go through the cycle decomposition algorithm. So the symmetric group Sn. Let's take an example. Here's a permutation in the two-line notation that I talked about last time. So this is saying it's a bijection from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5, or it's a permutation of the numbers 1, 2, 3, 4, 5, where 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, and 5 goes to 4. So what is this cycle decomposition algorithm about? You start with the smallest number that hasn't already been assigned to a cycle. In this case, it's 1. Where does 1 go? It goes to 2. 2 has to go somewhere. Where does it go? It goes to 3. Then 3 goes back to 1. So now we have what's called a cycle of size 3. We have these three things. As you apply sigma over and over and over, sigma of 1 is 1, sigma of 1 is, sigma of 1 is 2, sigma of 1 is 3, sigma of 1 is 1, and you just go round and round among these three elements. So you pick the smallest element that hasn't been assigned, in this case 4. 4 goes to 5, 5 goes back to 4. If you apply this permutation over and over and over, 4 and 5, 4 and 5, 4 and 5 just orbit back and forth. Cycle notation is you just write down these cycles in some order. The cycle 1, 2, 3 times the cycle 4, 5. So what does this cycle 1, 2, 3 really mean? That notation means we're taking the permutation that sends 1 to 2, 2 to 3, 3 back to 1, and fixes everything else. Okay, so it's easy to see from the cycle decomposition algorithm that multiplication of disjoint cycles commutes, that 1, 2, 3 times 4, 5 is the same as 4, 5 times 1, 2, 3. So why? What's going on with this product is it's really composition of functions. And what this is saying is, first we're going to switch 4 and 5, then we're going to cycle around 1, 2, and 3. We get the same permutation as if we cycle around 1, 2, and 3, and then switch 4, 5. Because these cycles are disjoint, they have nothing to do with each other. So like how 4 and 5 move around has nothing to do with how 1, 2, and 3 move around. So it doesn't matter in what order you permute these two disjoint pieces. Okay, what is the important fact? Every permutation in Sn can be written as a product of disjoint cycles. That product is basically unique up to the order of factors. So if you understand the cycle decomposition algorithm, it's sort of clear why this is true. So there's a special kind of cycle that I want to talk about called a transposition, which is a permutation that switches two things and leaves everything else exactly where it is. So say it switches I and j. So let's look at something like 1, 2 times 1, 3. How do you determine what this is? Well, 1 gets sent somewhere. So 1 goes to 3. First, we work from right to left, right? When you're composing functions, you first do the one on the right, then you do the one on the outside. So 1 goes to 3, then 3 doesn't get moved by this thing over here. So whatever happens in this permutation, 1 goes to 3. So what happens to 3? So 3 goes to 1, and then 1 goes to 2. So 3 gets sent to 2. What happens to 2? Well, 2 doesn't play in the first one, so 2 is still at 2. And then 2 goes to 1. So 1 goes to 3 goes to 2. 2 goes back to 1, so we just close up this cycle. One more example. What if we do the product in the other order? Well, same idea. 1 goes somewhere. 1 goes to 2. Then 2 doesn't move. So 1 goes to 2. 2 goes to 1. Then 1 goes to 3. So 2 goes to 3. 3 doesn't move in the first one. And then 3 goes to 1. So 3 goes back to 1. So what are we saying? We're seeing that multiplication here is not commutative. So this is non-abelian. Whenever n is greater than or equal to 3, because you could always just pull out these two transpositions and multiply them in either order. So it's easy to see that Sn is not abelian when n is at least 3 by working directly with two special transpositions. So I'm going to pause and erase, and then talk a little bit more about transpositions and a presentation for Sn. So we've just seen that when n is at least 3, Sn is non-abelian, because we could take the particular transpositions 1, 2 times 1, 3 and compare to 1, 3 times 1, 2. So the next thing I want to say is about the size of this group Sn. It's n factorial. And why is that? Well, it's the group made up of all bijections from 1 up to n to 1 up to n. So you have n choices for where to send 1. And then whatever choice you make, maybe you send 1 to 1, maybe you send 1 to 7, doesn't matter. There's n minus 1 choices left for where to send 2. You already picked some number for where you sent 1, and it's a bijection, so you can't use that number again. So there's n minus 1 choices for your next number, n minus 2 choices for your next number. All these choices are independent, so altogether there are n factorial of these bijections. Okay, that means S3 has size 6, D3 has size 6. These groups are isomorphic. It's easy to see why that's true. What is D3? It's the permutations of the vertices of a triangle. And if you just take your 3 rotations and your 3 reflections, you'll see that you can get every one of the 6 permutations. So D3 is S3 because it really is all the permutations of the numbers 1, 2, 3. Okay, but Sn and Dn are not going to be isomorphic ever again after that, because I'm using D2n for notation. S3 is isomorphic to D6. D2n has size 2n, and Sn has size n factorial. So 2n is just not equal to n factorial ever again. Okay, Sn is generated by transpositions. That is, every permutation can be written as a product of transpositions. Now, I'm no longer claiming that there's any kind of uniqueness here. There isn't, right? Like, there's a lot of ways that you can write the identity as a product of transpositions. It's the product of no transpositions, or it's the product 1, 2 times 1, 2, right? So how do we show that this is true? So we only need that every cycle is a product of transpositions, because we know that every permutation is a product of disjoint cycles. So the easiest way to see that every cycle is a product of transpositions is just to do it. So what I would do is I would take the cycle 1, 2, 3 and write it as a product of transpositions, and then take the cycle 1, 2, 3, 4 and write it as a product of transpositions. But I already did that on my scratch paper before filming this. So I'm just going to jump to the end. Let's take the cycle where A1 goes to A2, goes to A3, up to AK, and then comes back. Well, I'm just going to figure out what I want this product of transpositions to look like from right to left. So I know that I want A1 to go to A2. And then that's where I want A1 to end up. So I don't want A2 to ever move again. So if A1 times A2 is my first transposition, A1 is going to go to the right place if A2 never shows up again in here. Okay, so my rule for myself is no more A2s. So where does A2 go? Here, A2 has gone to A1, but we want A2 to go to A3. So I want to fix that. A2 is in the wrong place. So the next thing I want to include is A1. I want to go to A3. And then now A2 is in the right place. A2 went to A1, and then it went from A1 to A3. So A2 went to A3. So I never want another A3 in here. I don't want A3 to move. So no A2s, no A3s. But I want to fix where A3 went. A3 went to A1, but it should go to A4. So I'll get an A1, A4. And continuing in this way, you see that if you write A1, A4, A1, A5 in this order, you get this cycle written as a product of transpositions. Okay, so that's maybe not so enlightening, but I'm trying to explain to you how I think about seeing that this fact is true by moving elements one at a time. Something stronger is true. not only is it true that Sn is generated by transpositions, but Sn is generated by a special subset of transpositions where I gets switched with I plus 1. Transpositions, sigma I, which is just going to be I, gets exchanged with I plus 1. And what is I? This is where I goes from 1 to n minus 1. So what do we need to do? We need to show that these sigma i's generate all permutations. So it's enough to see that they generate all cycles. But we already saw that you could write all the cycles as products of transpositions. So we need only show that these special transpositions generate all the other transpositions, I, j. So just to give one example, and you can think about how to do this in general, the transposition 1, 3, well, it's not one of these special transpositions, but it is a product of them. 1, 2, 2, 3, 1, 2. Okay, so you can think about how to do this in general. So the very last thing I want to show you here, and I have just enough space, is something that I'm claiming is a presentation of Sn. So Sn, yeah, let me write it here. So Sn is generated by these sigma i's where they're all transpositions. So if you square, you get 1. So sigma I squared is 1. And sigma I sigma j equals sigma j sigma I if j is not equal to I plus or minus 1. Because then these special sigma I transpositions, these will be products of disjoint cycles, so they'll commute. So the very last thing that I need is what happens when j is equal to I plus or minus 1. And let me see if I have just enough space for this. Oh, terrible style. Sigma I plus 1 sigma I is the same thing as sigma I plus 1 sigma I plus 1. You can check that this is true. I apologize that this is very hard to see. This is a presentation for Sn, and actually proving that it's a presentation for Sn is pretty painful and not the kind of thing that I would ask you to do. So what I want to emphasize here is this idea of every permutation is a product of disjoint cycles. Cycles can all be written as products of transpositions, and in fact as products of these special transpositions. So I'm going to stop here, and in the last video we'll talk a little more about the structure of the set of all subgroups of a group and this nice visual way of representing it.